So, here's something worth noticing before we even begin. Right now, wherever you're lying, gravity is pressing you into the mattress. You've stopped fighting it. Your shoulders have sunk in. Your head has found its spot on the pillow. And that pull, that steady, patient tug toward the center of the earth, is one of the oldest mysteries human beings ever tried to solve. And for almost the entire span of our existence as a species, nobody had the faintest idea what it actually was. There's light in the room right now, too, even if it's dim. Maybe a hallway glow slipping under the door. Maybe the last dying charge of a phone screen somewhere on the nightstand. That light is real. It's made of something. It travels. It has a speed. And for most of human history, nobody knew that either. And underneath all of it, quietly, is your own heartbeat, doing what it's done every second since before you could form memories, powered by chemistry, that is, when you get down far enough, powered by physics. The warmth under the blankets, the faint hum of a building settling, all of it, every part of the ordinary, unremarkable experience of lying in the dark right now, is the end product of a conversation that has been going on for about 2,500 years. A conversation between curious, stubborn people and the universe itself. People asking simple questions. Why does that fall? Why does that glow? Why does that stay together? And the universe, slowly, reluctantly, giving up its answers, a little at a time, usually to the wrong person first, and only later to someone who could actually make sense of it. That's what we're doing tonight. We're going to walk through the entire story. 2,500 years, start to finish. Thales guessing that everything is secretly water. Newton alone in a plague year, terrified and brilliant. Einstein as a board patent clerk. All the way up to a photograph of a black hole and a mystery about the birth of the universe that nobody has solved yet. We're going to take it slow. There is no test at the end of this, no quiz, nothing to remember. If you drift off in the middle, that's completely fine. The ideas will still be here tomorrow, still true, still patient. The way physics has always been patient with us. Some of this might make more sense anyway when your mind is loose and unfocused, half tipped over into sleep, not trying so hard to force everything into tidy boxes. Because that's actually the first thing you should know about this whole story before we start. The universe doesn't owe us a tidy box. It doesn't owe us an intuitive picture that fits neatly into the kind of common sense you built up as a toddler learning to catch a ball. It only owes us consistency, and it has kept that promise for 2,500 years, more faithfully than anything else we know. So let your eyes close if they haven't already. Let your breathing settle into whatever rhythm it wants. And let's start at the very beginning, in a part of the world you might not expect, on the edge of the Aegean Sea, with a man who looked at the world around him and decided that underneath everything, hiding beneath all the noise and variety of daily life, there had to be one single simple thing that explained it all. That man's name was Thales, and he lived in a Greek city called Miletus, on the coast of what's now Turkey, sometime around the year 600 BCE. And here's what makes Thales worth starting with. He wasn't a priest. He wasn't claiming that the gods moved the sun or that Poseidon shook the earth in anger. He was doing something genuinely new, something we don't even have a good word for because it's become so normal to us now. He was looking at the physical world and trying to explain it using physical causes. No myths, no divine moods, just matter and its behavior. Thales proposed that everything, every substance, every object, every living thing, was ultimately made of water in different forms. It sounds almost silly today, but think about what he was actually doing. He'd noticed that water can be solid, liquid, or vapor. He'd noticed that living things need it, that the earth seems to float on it, that it's everywhere you look if you look carefully enough. He took a real observation and extended it into a universal principle. He was wrong about the specific answer, but he was right about the method, and the method is the whole point. Thales is usually credited as the first person in the Western tradition to ask, what is the one basic stuff that everything else is made of? And just that question, asked out loud, seriously, is arguably where physics begins. Other thinkers picked up the thread and pulled it in different directions. Anaximander, a student of Thales, decided the fundamental substance couldn't be any one familiar thing like water, because water itself needed explaining. He proposed something more abstract, an undefined, boundless substance he called the apeiron, out of which everything else separated. It's a strange, almost mystical idea, but notice the pattern. Each thinker is trying to get one level more fundamental than the last. That instinct, keep asking what's underneath the thing you just found, never really goes away. It's the same instinct that, 2,500 years later, leads physicists to smash particles together at nearly the speed of light looking for what's underneath the particles they already know about. And then, around 460 BCE, a thinker named Democritus, working with his teacher Leucippus, proposed something that turns out to be almost unreasonably close to correct. He argued that if you kept cutting any piece of matter in half, again and again and again, you would eventually reach a point where you couldn't cut it anymore. A smallest possible piece. Indivisible. He called this piece atomos, which literally means uncuttable, which is of course where we get the word atom. Democritus believed these atoms were tiny, solid, indestructible, and came in different shapes and sizes, and that everything you see around you, every texture, every taste, every color, was just different arrangements and combinations of these tiny uncuttable bits moving through empty space. Think about how strange and lonely that idea must have sounded at the time. No divine plan, no underlying purpose, just atoms and the void, colliding and combining according to blind mechanical rules. Democritus didn't have any way to prove this. There was no microscope, no experiment he could run. It was a philosophical leap, built on pure reasoning rather than evidence. And it would sit there, and proven, for well over 2,000 years, until the early 20th century finally vindicated him in ways he could never have imagined. Meanwhile, over on the other side of the Greek world, on the island of Samos and later in southern Italy, a rather different kind of thinker was chasing a rather different kind of truth. Pythagoras, yes, the triangle guy, believed that the deepest truth about the universe wasn't a substance at all. It was number, mathematics. He and his followers noticed something that must have felt almost supernatural at the time. If you pluck a string and then pluck a string exactly half its length, you get a note 1 octave higher, a note that sounds, to the human ear, like almost the same note. And if you use a string 2/3 the length, you get a different pleasing harmony. The relationships between pleasing musical sounds could be captured by simple whole number ratios. Music, this thing that seemed emotional, mysterious, almost magical, was secretly obedient to arithmetic. And the Pythagoreans took that discovery and ran with it, proposing that the whole cosmos, the motion of the planets, the structure of matter, everything, was built on hidden numerical harmony. They were, again, wrong about most of the specifics. But this idea, that mathematics isn't just a tool for describing nature, but is somehow woven into the actual structure of nature, becomes one of the most productive ideas in the entire history of physics. Every equation we're going to talk about tonight, from Newton's law of gravity to Einstein's field equations, is a direct descendant of that strange, half-mystical Pythagorean intuition. But if you had to pick one person from the ancient world whose ideas actually shaped physics for the longest stretch of time, it wouldn't be Thales or Democritus or Pythagoras. It would be Aristotle, born in 384 BCE, student of Plato, tutor to Alexander the Great, and quite possibly the single most influential thinker in the entire history of Western science, for better and for worse. Aristotle built an entire physical system, and it's worth understanding it a little, because the thing that makes it interesting isn't that it was foolish. It felt, to educated people for close to 2,000 years, obviously correct. Aristotle believed that everything on Earth was made of 4 elements: earth, water, air, and fire, and that each element had a natural tendency, a kind of built-in desire, to move toward its natural place. Heavy things, made mostly of earth, wanted to fall toward the center of the universe, which Aristotle believed was the center of the earth itself. Light things, like fire and smoke, wanted to rise. That's why a rock falls and a flame rises. Not because of some external force acting on them, but because that motion was simply built into what they were. And crucially, Aristotle believed heavier objects fell faster than lighter ones, because they had a stronger natural desire to reach their resting place. It's intuitive. It matches a very casual, everyday observation. Drop a hammer and a feather at the same time, and yes, the hammer hits the ground first. Case closed, as far as most people were concerned, for 18 centuries. Aristotle also drew a sharp line between the physics of Earth and the physics of the heavens, and this distinction mattered enormously. He believed the celestial realm, the sun, moon, planets, and stars, was made of a fifth, perfect, unchanging element, sometimes called ether, and that celestial objects moved in perfect circles forever, because circular motion was the most perfect, most natural motion there was. No friction, no decay, no need for any pushing force to keep them going. Down here on Earth, things were messy, corruptible, always slowing down and coming to rest unless something kept pushing them. Up there, in the heavens, everything was eternal and flawless. Two different sets of rules for two different realms. And this framework, this entire cosmology, got absorbed into medieval Christian, Islamic, and Jewish theology almost seamlessly, because it fit beautifully with the idea of an earth at the center of creation and a perfect, unchanging heaven above. Aristotle's physics wasn't just a scientific theory. It became part of the intellectual furniture of an entire civilization, taught in every university, defended by the church, assumed by nearly every educated person in Europe and the Islamic world. And here is the detail that matters most for where we're headed tonight. Nobody seriously challenged the core of it for roughly 1800 years. Not because people stopped thinking. Brilliant work happened in the meantime, especially in the Islamic Golden Age, where scholars like Ibn al-Haytham did remarkable experimental work on optics and light. But the basic architecture Aristotle built, heavy things fall because they want to, the heavens are perfect and unchanging. The earth sits still at the center of it all. That architecture held. It held until a stubborn, difficult, brilliant man in Pisa started dropping things and rolling things down ramps and looking through a new kind of tube at the sky and discovering that almost none of it was true. Let's go there slowly, because this is where the story really starts to move. And it starts, actually, not with Galileo at all, but with a quiet, cautious church administrator in Poland named Nicholas Copernicus, who spent decades of his life on a calculation he was almost afraid to publish. Copernicus was troubled by something inside Aristotle's system, refined over the centuries into an elaborate mathematical model by the astronomer Ptolemy. The Ptolemaic system had the Earth sitting still at the center of everything, with the sun, moon, planets, and stars all circling around it. And it worked, in the sense that it could predict where the planets would appear in the sky reasonably well. But it needed an increasingly absurd amount of mathematical patchwork to do it. Planets didn't just move in simple circles around the Earth. They moved in circles upon circles, tiny loops called epicycles riding on top of bigger circles, added one after another over centuries, purely to make the predictions match what astronomers actually observed. It was a system held together with duct tape, mathematically speaking, and Copernicus, sometime in the early 1500s, began to suspect that all of that ugly complexity would simply vanish if you made one radical assumption. What if the Earth wasn't the center after all? What if the Earth, and all the other planets, orbited the Sun instead? Copernicus worked out the mathematics carefully, privately, terrified of the reaction it might provoke, both from the Church and from the entrenched intellectual authority of Aristotle and Ptolemy. He didn't publish his full theory, a book called On the Revolutions of the Heavenly Spheres, until 1543, and legend has it he received the first printed copy on his deathbed. It's a poignant image, a man handing over an idea that would eventually topple 2,000 years of settled belief, too weak by then to see what would come of it. And what came of it, at first, was not much. Copernicus's model was elegant mathematically, but it wasn't obviously better at predicting planetary positions than Ptolemy's, and it demanded that people accept something wildly counterintuitive, that the solid, unmoving ground beneath their feet was actually hurtling through space at tremendous speed while spinning like a top. Most educated people simply didn't believe it. It took someone willing to physically demonstrate that Aristotle's whole picture of motion was wrong, and someone willing to point a new kind of instrument at the sky and see things no human eye had ever seen, to turn Copernicus's quiet mathematical suggestion into an unstoppable revolution. And that someone was Galileo Galilei, born in Pisa in 1564, a man with a talent for irritating powerful people almost as impressive as his talent for physics. Galileo's first great contribution didn't involve the sky at all. It involved rolling balls down ramps, right here on the ground. And in doing so, he demolished one of Aristotle's oldest and most trusted assumptions. Remember, Aristotle said heavier objects fall faster because they have a stronger natural tendency toward their resting place. Galileo doubted this, and being Galileo, he didn't just argue about it philosophically, he tested it. The popular story has him dropping 2 different weights from the Leaning Tower of Pisa and watching them hit the ground at the same time. And while historians debate whether that particular experiment actually happened exactly that way, we know for certain that Galileo did something even cleverer and more rigorous. He rolled balls down gently inclined ramps and carefully measured how far they traveled in equal intervals of time, using his own pulse, and later a water clock, to keep track. By slowing motion down using a gentle incline instead of a sheer vertical drop, he could actually measure the pattern of acceleration precisely, something impossible to do with something falling too fast for the human eye or the crude clocks of the era to track. And what he found was that objects, regardless of their weight, accelerate at exactly the same rate under gravity, and that the distance covered increases with the square of the time elapsed. Twice the time, 4 times the distance. 3 times the time, 9 times the distance. A clean, precise mathematical law hiding inside something as ordinary as a ball rolling down a slope. Aristotle's intuitive but wrong idea, heavier falls faster, was simply not true, and Galileo had the careful, repeatable measurements to prove it. Then, around 1609, Galileo heard about a new Dutch invention, a tube with lenses that made distant things appear closer, and he built his own improved version and turned it toward the sky. What he saw through that telescope broke Aristotle's cosmology into pieces almost immediately. He saw that the moon wasn't a smooth, perfect celestial sphere as Aristotle's philosophy demanded, but a rough, cratered, mountainous world, not so different from the Earth itself. He saw that Jupiter had 4 moons of its own, tiny points of light that visibly changed position from night to night, orbiting Jupiter the way the moon orbits Earth, which meant, obviously, that not everything in the heavens circled the Earth. He saw that Venus went through phases, just like our moon does, crescent to full and back again, and crucially, the way those phases changed only made sense if Venus was orbiting the Sun, passing sometimes on the near side of it and sometimes on the far side, exactly as Copernicus's model predicted, and completely inconsistent with the old Earth-centered system. He even saw sunspots, dark blemishes on the supposedly perfect, unchanging surface of the Sun. Piece by piece, observation by observation, the heavens Aristotle described as flawless and eternal turned out to be pockmarked, changing, imperfect, and very much made of the same kind of stuff as the Earth. This did not go over well with the authorities of the time. Galileo's outspoken defense of the Copernican system, and his tendency to phrase his arguments in ways that seemed to mock those who disagreed with him, brought him into direct conflict with the Catholic Church. In 1633, at the age of 69, he was tried by the Roman Inquisition, forced to publicly recant his statement that the Earth moves around the Sun, and sentenced to house arrest for the remainder of his life. Legend has it that as he rose from his knees after the forced recantation, he muttered under his breath, "And yet it moves," referring to the Earth, though most historians think this particular detail was added later, a little too perfect to be entirely true. What is true is that Galileo spent the last 9 years of his life confined to his villa outside Florence, going blind, but still working, still writing, producing during that period of house arrest one of his most important books, laying out the mathematical foundations of motion that would later feed directly into the work of a young Englishman born, in a small coincidence historians love to mention, in the very same year that Galileo died. But before we get to that Englishman, there's one more figure from this era we need to sit with for a while, because his story is one of the strangest and most human in this entire history, and his results were, in a very real sense, more immediately useful than Galileo's. His name was Johannes Kepler, and he was, by nearly every account, a deeply mystical thinker, driven as much by a belief in cosmic harmony and divine geometric perfection as by anything we'd recognize as modern scientific method. And yet, through some combination of extraordinary mathematical persistence and sheer stubborn honesty about his data, he arrived at 3 laws of planetary motion that were, and remain, exactly correct. Kepler was born in 1571 in what's now Germany, a sickly child from a troubled family, his father a mercenary soldier who abandoned the family, His mother later tried for witchcraft, a charge Kepler himself had to help defend her against. He became fascinated early on with the idea that the universe was built according to a hidden geometric plan reflecting the mind of its creator, and he spent years chasing an idea that seems almost embarrassingly mystical to modern ears, that the spacing of the 6 planets known at the time could be explained by nesting the 5 perfect Platonic solids, the cube, the tetrahedron, and so on, one inside another, like a set of cosmic Russian dolls. It was wrong, completely wrong. But it drove him to Prague, to work as an assistant to the great Danish observational astronomer Tycho Brahe, who had spent decades compiling the most precise naked-eye measurements of planetary positions ever recorded. When Tycho died in 1601, Kepler inherited this extraordinary trove of data, and he spent years, agonizing, painstaking years, trying to make the orbit of Mars fit a perfect circle, because circles were supposed to be the natural, perfect shape of celestial motion, a belief going all the way back to Aristotle. And no matter how he adjusted the numbers, the circle stubbornly refused to match Tycho's precise observations. The discrepancy was small, just 8 arcminutes, a gap so tiny that a less honest or less careful astronomer might have simply ignored it, chalked it up to measurement error, and published the circular orbit anyway. Kepler refused. He trusted Tycho's data more than he trusted his own mystical assumptions about perfect circles, and that trust in the evidence over his own preferred beliefs is, arguably, one of the most important moments in the entire history of science. Kepler eventually abandoned the circle entirely and discovered that Mars, and every other planet, actually moves in an ellipse, a squashed oval, with the Sun sitting not at the center, but at one of the 2 focus points of that oval. This became his first law. His second law described how a planet sweeps out equal areas in equal times as it orbits, moving faster when it's closer to the Sun and slower when it's farther away, which explained, elegantly, why planets don't move at constant speed the way the old circular model demanded. And years later, in 1619, after further obsessive calculation, he arrived at his third law, a precise mathematical relationship between how long a planet takes to orbit the Sun and how far away it is. These 3 laws, published between 1609 and 1619, were exactly right, verified over and over by every subsequent measurement for the next 4 centuries, derived by a man who believed, right up until his death, that he was uncovering the literal geometric music of the divine mind. Kepler gave physics something Aristotle's philosophy and even Galileo's mechanics hadn't yet provided: precise, predictive, mathematical laws for exactly how the planets move. It's worth sitting for a moment with just how unusual Kepler's honesty really was, because it's a quality that shows up again and again at the pivotal moments in this story. He had spent years of his life, and an enormous amount of intellectual effort, trying to prove that planetary orbits were perfect circles, a belief tied up with his own deep religious conviction that a perfect creator would only build with perfect shapes. When the data refused to cooperate, by a gap so small that almost nobody else would have noticed or cared, he didn't quietly round the numbers to fit his belief. He let the data win, and in doing so, discarded an idea he had loved, built his career around, and genuinely believed reflected the mind of God. That single act, trusting careful measurement over cherished belief, appears over and over in the story we're telling tonight. And every time physics takes one of its biggest leaps forward, that's usually the moment it happens, someone refusing to look away from a small, inconvenient number. What was still missing? The piece that would connect Galileo's falling balls on Earth to Kepler's orbiting planets in the heavens, uniting the physics of the ground and the physics of the sky into a single set of rules for the very first time, was waiting for a solitary, difficult, almost frighteningly brilliant young man who would spend 2 mysterious plague years locked away in the English countryside, and come out the other side having reinvented physics itself. That young man was Isaac Newton, born on Christmas Day in 1642, in a small manor house in Woolsthorpe, England, premature and so small that his mother later said he could have fit inside a quart mug. He was raised largely by his grandmother after his mother remarried, a lonely, difficult childhood that seems to have shaped a personality that stayed guarded, suspicious, and intensely private for the rest of his life. He went to Cambridge as a young man, and then, in 1665, The university closed its doors because of an outbreak of bubonic plague sweeping through London and the surrounding towns. Newton, 23 years old, retreated to his family's farm in Woolsthorpe, and over the following 2 years, isolated from his teachers, largely left alone with his own thoughts, he did something almost impossible to fully comprehend. He laid the groundwork for calculus, the mathematics of continuous change. He conducted experiments with prisms that revealed white light is actually a mixture of all the colors, splitting apart and recombining in ways nobody had properly understood before. And he began working out the mathematics of motion and gravitation that would eventually unify Galileo's falling balls with Kepler's orbiting planets. Newton himself, much later in life, referred to this period as the prime of his age for invention, and it's genuinely one of the most productive isolated stretches of intellectual work by a single person in recorded history. Now, about the apple. You've almost certainly heard the story. An apple falls on Newton's head, and inspiration strikes instantly. Gravity, eureka, done. The real story is both less dramatic and more interesting. Newton himself, in his old age, told several people, including the antiquarian William Stukeley, that the idea did come to him while watching an apple fall in the garden at Woolsthorpe during those plague years, and that the sight of it made him wonder why the apple always fell straight down toward the center of the earth, rather than sideways or upward. But there's no evidence the apple actually struck him on the head, and more importantly, seeing an apple fall didn't hand him a complete theory of universal gravitation on the spot. What it seems to have done is spark the specific, unusual question that would occupy him, on and off, for the next 20 years, which was this. The apple falls because Earth's gravity pulls it. But gravity clearly reaches high up into a tree. Does it reach as far as the moon? Could the very same force that pulls an apple to the ground also be the force that keeps the moon in its orbit around the Earth, rather than flying off in a straight line into space? That was the genuinely radical leap, not a flash of instant insight, but the slow, patient realization that the physics of the heavens and the physics of the ground might be one and the same physics, governed by one and the same law. Newton actually worked out rough calculations relating to this idea during the plague years, but he set the problem aside for almost 2 decades, distracted by other pursuits, including a long and secretive obsession with alchemy and biblical chronology that he kept hidden from public view for his entire life, work that, honestly, occupied more of his private writing than physics ever did. It took the persistent prodding of the astronomer Edmund Halley, who visited Newton in 1684 specifically to ask him a question about orbital mechanics that other prominent scientists of the day, including Robert Hooke, had been unable to solve, to pull the full theory back out of him. Halley asked Newton what shape of orbit would result if the force of gravity fell off with the square of the distance. Newton, almost casually, replied that it would be an ellipse, exactly the shape Kepler had discovered decades earlier through painstaking observation. Halley, astonished, asked how Newton knew this. Newton said he had calculated it years before, but couldn't immediately find the paper. Halley urged him to work it out again, and to write the whole thing up properly, and this request set Newton on an 18-month period of intense, obsessive labor. The result, published in 1687 with Halley personally funding the printing costs, was a book titled Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy, usually just called the Principia, and it is, without much serious competition, the single most important book in the history of physics. In the Principia, Newton laid out 3 laws of motion that are still taught in classrooms today, essentially unchanged. The first law says an object at rest stays at rest, and an object in motion stays in motion at a constant velocity in a straight line, unless acted upon by an outside force. This is a direct, cleaned-up descendant of ideas Galileo had been circling around, the recognition that steady motion requires no explanation, only changes in motion do. The second law gives this idea mathematical teeth, stating that the force acting on an object equals its mass multiplied by its acceleration, a deceptively simple equation. Force equals mass times acceleration. That turns out to be powerful enough to describe the motion of literally everything from a thrown ball to a comet. And the third law, for every action there is an equal and opposite reaction, explains why a rocket can push itself forward by expelling gas backward, why you can walk forward by pushing backward against the ground, why the earth pulls you down exactly as hard as you pull the earth up, even though only one of those pulls has any noticeable effect given the difference in mass. And then, building on these three laws, Newton introduced universal gravitation, the single equation that finally, genuinely, unified the heavens and the earth. Every object with mass, he proposed, attracts every other object with mass, with a force that grows stronger the more massive the objects are, and weaker the farther apart they are, weakening specifically with the square of the distance between them. The apple and the earth and the moon, the sun and every planet orbiting it, all governed by exactly the same equation, exactly the same force, acting across empty space with no visible mechanism connecting them at all, an idea that troubled some of Newton's contemporaries deeply, since it seemed to require some kind of mysterious action at a distance that nobody could explain, only describe. But the mathematics worked. It worked so precisely that using Newton's law of gravity, astronomers could predict the return of comets, explain the tides as the pull of the moon and sun on the oceans, and, decades later, even predict the existence of an entirely undiscovered planet, Neptune, simply by noticing small irregularities in the orbit of Uranus that could only be explained by the gravitational tug of something unseen. Further out, Newton had given the universe a rulebook, and the rulebook kept turning out to be right. It's worth pausing here to say something honest about Newton the person, because the picture of the lone genius quietly working in isolated brilliance leaves out a less flattering but very real side of him. Newton was, by most contemporary accounts, secretive, thin-skinned, and at times genuinely vindictive toward those he saw as rivals. His long, bitter dispute with the German mathematician Gottfried Leibniz over who had truly invented calculus first turned into one of the ugliest priority disputes in the history of science, with Newton, from his position as president of the Royal Society, arranging for an official committee to investigate the dispute, a committee whose report he then largely wrote himself, unsurprisingly concluding in his own favor. His relationship with Robert Hooke, the scientist who had also been thinking about gravity and inverse square forces before Halley's visit, was similarly poisoned, and some historians believe Newton's famous, gracious-sounding line, "If I have seen further it is by standing on the shoulders of giants," was actually a subtly cutting jab at the notably short-statured Hooke, rather than the humble tribute it's usually taken to be. Newton also spent decades of his private life obsessively studying alchemy, searching for the philosopher's stone, and poring over biblical prophecy, trying to calculate the exact date of the apocalypse, work he kept largely hidden because it didn't fit the image of rigorous rational science he wanted associated with his public reputation. He was, in other words, a deeply strange, difficult, brilliant, and in some ways quite small man, and none of that complexity takes away from what the Principia actually accomplished. It's a useful thing to remember, actually, whenever the history of physics gets told as a clean parade of noble geniuses. The people who built this understanding of the universe were, almost without exception, just people, vain sometimes, petty sometimes, driven by ambition and rivalry and wounded pride as often as by pure curiosity. The physics turned out to be beautiful and true. The physicists were not always either of those things, and somehow, remarkably, that never stopped the work itself from holding up. Because what it accomplished was this. For the first time in human history, a single, coherent, mathematical framework could explain the fall of an apple, the arc of a cannonball, the orbit of the moon, the return of a comet, and the rise and fall of ocean tides, all with the same handful of equations. The universe, which had seemed for millennia to be governed by mysterious wills and divine tendencies and separate rules for the heavens and the earth, suddenly looked like a machine. A vast, precise, predictable clockwork mechanism. And if you knew the position and velocity of every particle in it at any given moment, in principle, you could calculate its entire future and its entire past with perfect certainty. This idea would later be pushed to its most extreme, most confident conclusion by the French mathematician Pierre-Simon Laplace, who imagined a vast intelligence that, knowing the exact state of every particle in the universe at one instant, could predict everything that would ever happen for all of time with absolute precision. For roughly 2 centuries after Newton, this clockwork universe, deterministic, mechanical, fully knowable in principle, was simply what physics was. It was solved, or so it felt. All that remained, most physicists believed, was to work out the details, refine the measurements, and mop up a handful of loose ends. It was a comfortable, confident era. It's worth pausing to notice just how strange this clockwork picture actually is, if you sit with it for a moment rather than rushing past it the way a textbook might. Newton's equations don't care about a preferred direction for time to run in, and they don't care whether you're calculating forward from the present into the future or backward from the present into the past. Feed them the position and velocity of everything in a system at any single instant, and they hand you back the entire history and the entire future of that system with, in principle, perfect certainty. There's no room in this picture for genuine chance, for anything happening for no determinable reason. Even something that looks random to us, a coin landing heads instead of tails, a die coming up 6, is, in Newton's universe, actually fully determined by the exact forces and positions involved, and only looks random because we don't have precise enough information to calculate it ourselves. This is the deterministic, clockwork vision that the French mathematician Laplace pushed to its logical extreme, and for roughly 200 years, most physicists genuinely believe the universe worked this way, all the way down. It's a comforting picture, in a strange sense, even if it leaves very little room for anything like free will. Everything has a cause. Everything follows a rule. Nothing is ever truly, fundamentally unpredictable, if only you knew enough. And it lasted, largely unchallenged in its foundations, until a quiet German physicist sat down to solve a stubborn little puzzle about the way hot metal glows and accidentally lit a fuse that would take physics apart and rebuild it from the ground up. But before we get to that fuse, we need to spend some time in the 18th and 19th centuries, because this is where physics quietly picked up two more threads that would later turn out to be the same thread, heat and electricity, and wove them into an understanding of the universe that felt, for a while, more complete and more triumphant than anything Newton could have imagined. Let's start with heat, because heat turns out to hide one of the strangest and most profound ideas in all of physics, the idea that time itself has a direction. The Industrial Revolution, all those steam engines pumping water out of mines and driving factory machinery, created an urgent practical question. How efficient can an engine possibly be? How much useful work can you extract from a given amount of heat? A young French military engineer named Sadi Carnot took up this question in 1824 in a slim book that almost nobody noticed at the time, and worked out something remarkable, a theoretical limit on how efficient any heat engine could ever be, no matter how cleverly it was built. Carnot showed that you could never convert heat completely into useful work. Some of it is always, unavoidably, lost. He died of cholera in 1832, only 36 years old, and much of his work was so far ahead of its time that it took decades for other physicists to fully appreciate what he'd found. The next piece came from an English brewer turned physicist named James Joule, who spent years in the 1840s conducting meticulous, almost obsessive experiments, using a paddle wheel churning inside an insulated container of water to show that mechanical work and heat were fundamentally the same kind of thing, interchangeable, convertible from one form to the other according to a precise, fixed ratio. This became the first law of thermodynamics. Energy can be converted from one form to another, but it can never be created or destroyed, only moved around and transformed. It's an elegant, satisfying law, a strict cosmic accounting rule. But it was a German physicist named Rudolf Clausius who, building on Carnot's earlier insight, uncovered something stranger and more unsettling in the 1850s. Clausius introduced a new quantity, one he called entropy, a measure, roughly speaking, of disorder or of how spread out and unavailable energy has become. And he showed that in any isolated system, entropy always increases, or at best stays the same. It never decreases. Heat flows from hot objects to cold ones, never spontaneously the other way. A dropped glass shatters into 1,000 pieces, and no matter how long you wait, those pieces never spontaneously reassemble themselves. This became the second law of thermodynamics, and it is, in a very real sense, the reason time seems to have a direction at all. Newton's laws of motion, remarkably, don't actually care which way time flows. If you filmed two billiard balls colliding and played the film backward, the backward version would still perfectly obey Newton's equations. But entropy breaks that symmetry completely. The universe, as a whole, is very slowly, very steadily, becoming more disordered, and that quiet, relentless increase in disorder is what gives us the felt experience of a past that's fixed and a future that's open, an arrow pointing in only one direction. Physicists still argue today about exactly why the universe started out in such an extraordinarily low entropy, highly ordered state to begin with, allowing all of this gradual disordering to unfold in the first place. It remains one of the deepest open questions in cosmology, quietly inherited from a Victorian-era physicist thinking about steam engines. While all of this was unfolding, another thread was developing almost entirely independently, the study of electricity and magnetism. And here we meet one of the most beloved figures in the entire history of physics, an Englishman named Michael Faraday, born in 1791 into genuine poverty, the son of a blacksmith, with almost no formal education. Faraday started his working life as an apprentice bookbinder, and it was through binding and reading the books passing through his hands that he taught himself the rudiments of science. He eventually talked his way into a position as a laboratory assistant to the famous chemist Humphrey Davy, and from that humble entry point, Faraday went on to become perhaps the greatest experimental physicist who ever lived, despite having almost no formal mathematical training at all. He thought in pictures, in physical intuitions, in what he called lines of force, invisible threads he imagined stretching through space around magnets and electrical charges, and this intuitive, visual, almost artistic way of thinking led him to genuinely revolutionary discoveries. In 1831, Faraday discovered electromagnetic induction, the fact that a changing magnetic field could generate an electric current in a nearby wire, a discovery that is, quite directly, the reason every electrical generator and every power plant on Earth works the way it does today. Faraday's lines of force, his intuitive picture of invisible fields filling space, were more than just a useful mental trick. They turned out to be a genuinely deep insight into the structure of reality, though it would take a much more mathematically trained mind to prove it. That mind belonged to a Scottish physicist named James Clerk Maxwell, born in 1831, the same year as Faraday's great discovery, a man whose talents combined the intuitive brilliance of Faraday with a mathematical sophistication Faraday himself never possessed. Maxwell took Faraday's pictures of invisible field lines and translated them into precise mathematical language, and in doing so, in a series of papers published through the 1860s, he accomplished something almost unbelievable. He showed that electricity and magnetism, two forces that had seemed distinct throughout all of human history, were actually two faces of a single underlying phenomenon, the electromagnetic field, and he captured the entire behavior of that field in a compact, elegant set of four equations. And then, working through the mathematical consequences of his own equations, Maxwell discovered something nobody had expected at all. His equations predicted that a disturbance in the electromagnetic field, a ripple, would propagate through space as a wave, and when he calculated the speed of that wave using purely electrical and magnetic quantities measured in laboratories with no reference to light whatsoever, the number that came out matched, almost exactly, the already known measured speed of light. Maxwell realized, with what must have been a genuinely thrilling jolt of understanding, that light itself was an electromagnetic wave, the very same phenomenon his equations described. Electricity, magnetism, and light, three things that had seemed utterly unrelated for the entire history of human thought, were revealed to be a single unified phenomenon, obedient to a single elegant mathematical structure. It's worth noticing, too, just how differently Faraday and Maxwell each arrived at the same underlying truth, because it's a pattern that repeats throughout this whole story. Faraday, self-taught, without much formal mathematics, thought in pictures, in curved lines stretching invisibly through the space around a magnet, and trusted his hands and his eyes more than any equation. Maxwell, formally trained, mathematically gifted almost from childhood, took those pictures and gave them precise numerical teeth, and in doing so found something Faraday's intuition alone could never have revealed, the exact speed at which a disturbance in the field would ripple outward, a number that happened to match the measured speed of light so closely that it couldn't possibly be coincidence. Two very different minds, one working from intuition and one from rigorous calculation, converging on the same deep truth from two different directions. It's a combination that shows up again and again in this story. The patient experimentalist and the careful mathematician, each incomplete without the other, together revealing something neither one could have found alone. By the final decades of the 19th century, physics felt, to nearly everyone working in the field, essentially finished. Newton had given mechanics and gravity. Maxwell had given electromagnetism and light. Thermodynamics explained heat and the arrow of time. The periodic table was filling in nicely. Atoms and molecules seemed well understood as tiny, solid, indestructible particles bouncing around according to Newton's laws. There's a famous, possibly apocryphal remark, sometimes attributed to the physicist Lord Kelvin, sometimes to Albert Michelson, that physics was essentially complete, that all that remained for future generations was to measure things to a few more decimal places, to polish the furniture in a house whose architecture had already been finished. It was a comfortable, confident, faintly smug era. And it was, as it turned out, spectacularly, gloriously wrong, because a handful of small, stubborn, seemingly minor problems were quietly sitting there, refusing to fit the beautiful architecture everyone believed was complete, and those small problems were about to blow the entire house apart. The first crack showed up in something almost comically mundane, the way hot objects glow. Heat a piece of metal in a forge, and it glows first a dull red, then orange, then yellow, and if you get it hot enough, a blinding white. This is called blackbody radiation, and by the 1890s physicists had very precisely measured exactly how much energy a hot object radiates at each frequency of light. They had beautiful, smooth experimental curves. And then they tried to explain those curves using the classical physics of Newton and Maxwell, and the answer they got was not just wrong, it was absurd. The classical calculation predicted that a hot object should radiate more and more energy as you move toward higher and higher frequencies, climbing without limit, toward violet, toward ultraviolet, all the way to infinity. Infinite energy pouring out of any warm object, which would mean, among other things, that your own body and a cup of coffee and everything else with a temperature above absolute zero should be blasting out lethal, unbounded radiation constantly. This obviously wasn't happening. The prediction earned a dramatic nickname, the ultraviolet catastrophe, and it wasn't a small error. It was catastrophically, fundamentally wrong, a sign that something in the foundation itself, not just the details, had gone badly astray. The second crack was quieter, but in some ways stranger, and it involved an experiment specifically designed to detect something that should have been easy to find and simply wasn't there. 19th century physicists, following the logic that every known kind of wave needed a medium to travel through, sound through air, ocean waves through water, assumed that light, since Maxwell had shown it to be a wave, must be rippling through some invisible substance filling all of space, which they called the luminiferous ether. And if the Earth was moving through this ether as it orbited the Sun, there should be a detectable ether wind, a tiny difference in the measured speed of light, depending on which direction you measured it, the same way you'd feel a breeze from running through still air. In 1887, the American physicist Albert Michelson, working with the chemist Edward Morley, built an exquisitely sensitive instrument specifically to detect this difference, splitting a beam of light into two perpendicular paths and looking for the faintest shift in how the two beams interfered when they recombined. They expected to find a small but measurable effect. Instead, they found nothing at all. No matter which direction they pointed their instrument, no matter the time of day or the season of the year, the speed of light came out exactly the same every single time. This was one of the most important null results in the history of science, a careful, rigorous search for something that, according to everything physicists believed, absolutely had to be there, and it simply wasn't. Physicists tried for years to patch this up without giving up on the ether entirely, proposing, among other things, that objects moving through it might physically shrink in the direction of their motion by just enough to hide the effect. A mathematically clever fix that nonetheless left the underlying mystery, why the ether seemed permanently, perfectly undetectable, completely unexplained. Both of these cracks share something important, something worth noticing before we move past them. In each case, careful, honest measurement refused to agree with a theory that almost everyone found intuitively obvious. The blackbody problem showed that treating energy as smooth and continuous, the way water pours, led to predictions of infinite energy that plainly couldn't be true. The ether experiment showed that a medium everyone assumed had to be there for light to wave through simply left no trace, no matter how sensitively anyone looked for it. Neither problem seemed, at first glance, like it would demand rebuilding physics from its foundations. They looked like small, technical embarrassments, the kind of thing a clever calculation might tidy up within a year or two. That is almost never how the deepest revolutions in physics announce themselves. They rarely arrive as thunderclaps. They arrive as small, stubborn, easily ignored discrepancies, tiny gaps between prediction and measurement that everyone assumes will be closed eventually by someone else, until one particular person, for reasons of temperament or curiosity or simple bullheadedness, decides to actually follow the gap all the way down instead of looking away from it. By the turn of the century, these two small, stubborn anomalies, one about glowing metal, one about the speed of light, sat there quietly, unresolved, mostly ignored by a physics community that considered its work essentially finished. Nobody at the time understood that these were not minor loose ends waiting to be tidied up with slightly better measurements. They were the first visible cracks in the entire foundation of classical physics, and within just a few years, a handful of people, starting with a cautious, deeply conservative German physicist who wanted nothing more than to understand the existing foundations a little more deeply, would follow those cracks all the way down and discover that underneath them was an entirely different universe, one built not on smooth continuity, but on something granular, probabilistic, and strange beyond anything Newton or Maxwell had ever imagined. That cautious German physicist was Max Planck, born in 1858, a man so thoroughly conventional in temperament that one of his own professors had advised him against studying physics at all, on the grounds that the field was essentially complete and there was nothing important left to discover. Planck ignored that advice, and in the year 1900, wrestling with the blackbody radiation problem, he found a mathematical formula that fit the experimental curves perfectly. But to make the formula work, he had to accept something deeply strange, that energy isn't smooth and continuous, the way everyone had always assumed, but comes in discrete, indivisible chunks, which he called quanta. Energy, it turned out, behaves less like water, which you can pour out in any amount, and more like sand, which looks smooth from a distance but is actually made of individual grains up close. Planck himself didn't believe this reflected anything real about the universe. He assumed it was a mathematical trick, a stopgap he expected some future physicist would eventually replace with a proper classical explanation. Nobody ever did. He had, without meaning to, lit a fuse that would take about 25 years to fully detonate. The person who picked up that fuse was a 26-year-old patent clerk in Switzerland named Albert Einstein, who in 1905, his so-called miracle year, published 4 papers, any one of which would have made a career, while working a day job reviewing other people's inventions because he couldn't secure an academic post. One of those papers explained a stubborn puzzle called the photoelectric effect, the fact that shining light on certain metals knocks electrons loose, but the energy of those electrons depends on the color of the light, not its brightness, something classical wave theory simply couldn't explain. Einstein's answer was that light itself, not just the matter absorbing or emitting it, comes in discrete packets, later called photons. This was bolder than even Planck had proposed, and it meant physics now had genuine, irreconcilable evidence that light behaves like a wave in some experiments and like a stream of particles in others, a deep strangeness now called wave-particle duality that nobody at the time knew how to resolve. Around the same period, physicists were also confused about the structure of the atom itself. In 1911, Ernest Rutherford, firing tiny charged particles at gold foil, discovered that atoms are mostly empty space, with almost all of their mass concentrated in a tiny, dense nucleus at the center, electrons presumably orbiting around it. But this picture had a fatal problem. Classical electromagnetism insisted that an orbiting, accelerating electron should continuously radiate away energy and spiral into the nucleus in a fraction of a second, meaning every atom in the universe should have collapsed almost instantly. Obviously, they hadn't. In 1913, the Danish physicist Niels Bohr resolved this by simply declaring that classical physics didn't apply inside the atom, that electrons could only occupy certain specific, quantized orbits, and while in those orbits, they didn't radiate at all, only jumping between orbits by absorbing or emitting a photon of precisely the right energy. It was a strange, seemingly arbitrary rule, but it predicted the exact pattern of light emitted by hydrogen gas with stunning precision, and strange rules that predict reality precisely tend to get taken very seriously. What followed, roughly from 1923 to 1927, is sometimes called the golden age of quantum physics, a period of astonishing creative intensity involving a cast of characters in their 20s and 30s working almost feverishly. A French aristocrat named Louis de Broglie proposed that if light, previously thought of as a pure wave, could behave like a particle, then perhaps particles like electrons could behave like waves too. An idea confirmed a few years later when electrons were shown to diffract exactly like light does. Werner Heisenberg, escaping his hay fever on a windswept, pollen-free island in the North Sea, built an entirely new mathematical framework based only on observable quantities, a framework that turned out, to his own initial unease, to obey strange rules where the order of multiplication actually mattered. Erwin Schrödinger, on a romantic retreat in the Swiss Alps, derived a wave equation describing how a mathematical object called the wave function evolves over time, a formulation so much more intuitive than Heisenberg's abstract tables that physicists embraced it eagerly, at least until Max Born pointed out that the wave function doesn't describe a real physical wave at all, but rather the probability of finding a particle in a given location. Before you measure a quantum system, in other words, there may simply be no definite fact about where a particle is. Measurement itself, in this view, doesn't reveal a pre-existing reality so much as create one. This idea troubled Albert Einstein profoundly, the same man who had helped start the whole revolution with his photon paper 20 years earlier. Einstein believed the universe had definite properties whether or not anyone was looking at it, and he spent years constructing clever thought experiments designed to show that quantum mechanics must be an incomplete description of a deeper, more sensible, deterministic reality. He debated these questions face-to-face with Niels Bohr at a series of invitation-only physics conferences in Brussels called the Solvay Conferences, trading elaborate hypothetical scenarios at breakfast, with Bohr spending each day working through the logic and finding, by dinner, the hidden flaw in Einstein's reasoning almost every single time. Einstein never managed to find a logical contradiction in quantum mechanics, though the deep discomfort he felt about it, particularly regarding a strange correlation between distant particles that quantum theory calls entanglement, and that Einstein dismissively called spooky action at a distance, would linger unresolved for decades. Eventually tested directly by experiment in the 1970s and 1980s, and quantum mechanics, every single time, was found to be correct. The universe really is that strange. It doesn't owe us an intuitive picture, only consistency, and consistency is exactly what it delivers. While quantum mechanics was unraveling the behavior of the very small, an entirely separate revolution was unfolding around the very large, and it began with a question a bored teenager in northern Italy asked himself around 1895. What would it look like to ride alongside a beam of light? That teenager, of course, was the same Albert Einstein, and a decade later, in that same miracle year of 1905, he answered his own question with the special theory of relativity, built on two simple, radical assumptions, that the laws of physics look the same to every observer moving at a constant velocity, and that the speed of light is the same for every observer, regardless of how fast they or the light source happen to be moving. Taking these two ideas seriously, rather than explaining them away, led Einstein to conclusions that felt almost impossible. That two events happening at the same time for one observer might not be simultaneous for another, that moving clocks run measurably slower, that moving objects measurably shrink along their direction of motion, and that space and time are not separate, fixed backdrops, but are woven together into a single four-dimensional fabric, space-time, whose shape depends on how you're moving through it. Special relativity, though only applied to objects moving at constant speed, and Einstein knew almost immediately that it left out the most universal force in the universe, gravity, which accelerates everything it touches. In 1907, he had what he later called the happiest thought of his life, the realization that a person in free fall feels weightless, unable to distinguish falling in a gravitational field from floating freely in empty space with no gravity at all. This equivalence between gravity and acceleration became the seed of an idea Einstein would spend the next 8 grueling years turning into a complete theory, that gravity isn't really a force pulling objects around at all, but a curvature in the fabric of spacetime itself, caused by the presence of mass and energy, with objects simply following the straightest available path through that curved geometry. Working out the precise mathematics of this idea nearly broke him, requiring him to learn an entirely unfamiliar branch of geometry with the help of a mathematician friend, and racing, in the final months of 1915, against the brilliant mathematician David Hilbert, who was closing in on the same equations from a different direction. Einstein finished first, presenting his completed general theory of relativity to the Prussian Academy of Sciences in November of 1915, and almost immediately used his new equations to explain a small, decades-old mystery in the orbit of Mercury that Newtonian gravity had never been able to account for. The numbers matched exactly, and Einstein later said his heart pounded with excitement for days afterward. The theory made an even bolder, more testable prediction, that gravity should bend the path of starlight passing near a massive object like the Sun by precisely twice the amount Newtonian physics would predict. In 1919, a British astronomer named Arthur Eddington led an expedition to photograph a total solar eclipse specifically to measure this bending. And when the results came back matching Einstein's prediction rather than Newton's, the announcement made front-page news around the world overnight, transforming Einstein from a respected physicist into a global icon almost instantly. General relativity went on to predict things far stranger than bending starlight. Buried inside an exact solution found by a physicist named Karl Schwarzschild, worked out remarkably while serving on the front lines of the First World War, was a hint that an object compressed densely enough could warp spacetime so severely that not even light could escape it, a possibility most physicists dismissed as a mathematical curiosity for decades, until careful theoretical work in the 1960s showed such collapse was essentially unavoidable under the right conditions, and later, observational evidence, culminating in the direct detection of gravitational waves from colliding black holes in 2015 and an actual photograph of a black hole shadow in 2019, confirmed that these strange objects, regions where the geometry of space itself becomes a one-way door, are absolutely real. And so, by the middle of the 20th century, physics found itself holding two extraordinarily successful theories: quantum mechanics, describing the strange, probabilistic behavior of the very small, and general relativity, describing the smooth, curved geometry of gravity and the very large, each confirmed by experiment after experiment to a level of precision that borders on the unreasonable. And yet, when physicists have tried to combine them, to describe what happens at the very center of a black hole, or at the very first instant of the universe's existence, when everything was compressed into a space far smaller than an atom, the two theories simply refuse to speak to each other. The mathematics breaks down into nonsensical infinities. Reconciling them into a single, deeper theory of quantum gravity remains one of the great unfinished projects in all of physics, a problem that has now sat open, stubbornly unresolved, for the better part of a century. There's one more idea from this period worth sitting with quietly for a moment, because it captures the strangeness of quantum mechanics better than almost anything else, and that's Heisenberg's uncertainty principle, worked out in 1927. It says that certain pairs of properties, like a particle's exact position and its exact momentum, can never both be known with perfect precision at the same time, not because our instruments are clumsy, but because nature itself doesn't have both values sitting there waiting to be measured. The more precisely you pin down where something is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of technology. It's a fact about the universe, and it means that at the smallest scales, reality is fundamentally, irreducibly fuzzy. Schrödinger, uneasy about where all of this probability talk seemed to be leading, once devised a now famous thought experiment involving a cat sealed in a box with a device that had a 50% chance of releasing poison, intending it as a criticism, a way of showing how absurd it would be if quantum superposition, existing in multiple states at once, applied to something as large as a cat, existing as neither definitely alive nor definitely dead until observed. He meant it as a reduction to absurdity. Instead, it became one of the most famous images in all of science, a strange, uncomfortable reminder of just how far quantum weirdness reaches before ordinary human intuition finally takes back over. And relativity, for its part, produces its own strange, deeply human consequence, one that's worth carrying with you as you drift towards sleep tonight. Because moving clocks really do run slow, and gravity really does bend time. A twin who travels near the speed of light and returns home really would be younger than the twin who stayed behind, not as a trick of measurement, but genuinely, biologically, fewer heartbeats actually having occurred. This isn't only a thought experiment either. It's baked into machinery you rely on every single day. The satellites that make up the global positioning system carry atomic clocks that tick very slightly differently than clocks on the ground. Faster because they sit higher up in Earth's gravitational field, slower because they're moving quickly relative to you. And unless engineers corrected for both of Einstein's effects, special and general relativity together, your phone's map would drift by miles within a single day. Somewhere above your head right now, while you lie here, satellites are quietly running on adjusted clocks so that a piece of physics born from a teenager's daydream about riding alongside a beam of light can tell you, later today, exactly where the nearest coffee shop is. Let's step back down from black holes and cosmic scales for a moment, back into the atom itself, because there's another whole story unfolding at the same time, deep inside the nucleus that Rutherford discovered back in 1911. Rutherford himself, working in Manchester and later Cambridge, became something like the father figure of an entire generation of nuclear physicists, and around him worked one of the most remarkable scientists in history, Marie Curie, who along with her husband Pierre had spent years in the 1890s processing tons of a mineral called pitchblende by hand, in a leaky shed. To isolate two new radioactive elements she named polonium, after her native Poland, and radium. Curie remains the only person ever to win Nobel Prizes in two different sciences, physics and chemistry, and her careful, dangerous work laid much of the experimental foundation for understanding radioactivity, the process by which unstable atomic nuclei spontaneously break apart, releasing energy and transforming into different elements entirely. For years after Rutherford's discovery of the nucleus, physicists knew it contained positively charged protons, but the numbers didn't quite add up. Nuclei seemed heavier than they should be if protons were the only thing inside them. In 1932, the English physicist James Chadwick, working in Rutherford's laboratory, discovered a new particle, electrically neutral, roughly the same mass as a proton, which he named the neutron. This single discovery explained the missing mass, explained the existence of different isotopes of the same element, and, within just a few years, opened the door to something with far darker implications, nuclear fission, the process by which a heavy nucleus like uranium, struck by a neutron, splits apart into smaller nuclei while releasing an enormous burst of energy. A discovery made in Germany in 1938 that would, within just a few years, lead directly to the Manhattan Project and the atomic bomb, a chapter of this story that's really its own long, difficult tale for another night. In the decades that followed, physicists kept smashing particles together at higher and higher energies, and kept finding more particles than anyone expected, a confusing, sprawling collection that at one point felt almost as messy as the periodic table had before quantum mechanics explained it. Slowly, through the middle of the 20th century, physicists worked out an underlying order to all of it, a framework now called the Standard Model of Particle Physics, describing all the known fundamental particles, quarks, which combine in threes to form protons and neutrons, electrons and their heavier cousins, and the force-carrying particles that transmit the electromagnetic, weak, and strong nuclear forces. The Standard Model made one final, crucial prediction that took nearly 50 years to confirm: the existence of a particle called the Higgs boson, tied to a field filling all of space that gives other particles their mass. In 2012, using the Large Hadron Collider, an underground ring 17 miles around straddling the border of France and Switzerland. Physicists finally detected it, the last missing piece of the Standard Model, confirmed exactly where the theory said it would be. It's worth lingering for a second on just how strange Rutherford's original discovery really was, because the strangeness of it echoes everything else we've talked about tonight. He and his team fired tiny, fast-moving charged particles at an impossibly thin sheet of gold foil, expecting them to pass through more or less undisturbed, the way a bullet passes through fog. Most of them did exactly that. But every so often, a tiny fraction of these particles bounced almost straight back the way they'd come, as if they'd struck something small, dense, and immovable. Rutherford later said it was as astonishing as firing a heavy artillery shell at a piece of tissue paper and having it bounce back and hit you. The only explanation was that almost all of an atom's mass was concentrated in an impossibly tiny core, with the rest of the atom, everywhere the electrons supposedly lived, being almost entirely empty space. The solid, firm feeling table under your hand, the floor holding up your bed right now, all of it, at the atomic level, is overwhelmingly nothing at all, held together not by any real solidity, but by electromagnetic forces between mostly empty atoms. The Standard Model that eventually emerged from all of this work organizes the fundamental building blocks of matter into a surprisingly small, elegant list. There are quarks, which combine in groups of 3 to form protons and neutrons, and there are leptons, a family that includes the electron along with its heavier, less familiar relatives, the muon and the tau, and a nearly massless, famously elusive particle called the neutrino, of which, incidentally, a few 100 trillion are passing harmlessly through your body every single second as you lie here, streaming in from the sun and from nuclear reactions across the galaxy, interacting with almost nothing on their way through. Binding all of these particles together are 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces that operate only across the tiny distances inside an atomic nucleus, holding protons together despite their mutual electrical repulsion, and governing the radioactive decay that powers the sun and lights up a Geiger counter. There's also antimatter to consider, predicted on purely mathematical grounds in 1928 by the reserved, almost supernaturally precise English physicist Paul Dirac, who found that his elegant equation describing the electron seemed to demand the existence of a mirror image particle with the same mass, but opposite charge, a prediction confirmed experimentally just 4 years later. Physics, again and again in this story, works this way. The mathematics, followed honestly and without flinching, keeps handing us things nobody asked for and nobody expected, and time after time, when we go looking, we find them sitting there in nature, exactly as the equations said they would be. The quarks themselves weren't discovered directly, since they never appear alone in nature, only bound together in 2s and 3s inside larger particles. But their existence was inferred in the 1960s by physicists including Murray Gell-Mann, who organized the growing zoo of particles being found in accelerators into tidy mathematical patterns, the same way Mendeleev had once organized the elements into the periodic table decades before anyone understood why atoms behaved the way they did. Gell-Mann borrowed the name quark from a line in James Joyce's novel Finnegan's Wake, a small, playful detail that captures something true about physics at its best, that even the most rigorous, mathematically precise science is still, underneath everything, a very human, sometimes whimsical activity, carried out by particular people with particular senses of humor, working late into particular nights, trying to make sense of a universe that owes them nothing but consistency. Let's zoom all the way back out now, from the tiniest particles to the largest possible scale there is, the universe as a whole, because this is where the story of general relativity and the story of astronomy finally merge into something genuinely awe-inspiring. When Einstein first applied his new equations to the universe as a whole in 1917, he ran into a problem. The equations refused to describe a static, unchanging universe, the kind everyone at the time simply assumed we lived in. So Einstein added an extra term to his own equations, a cosmological constant, purely to hold the universe still, an adjustment he would later call the biggest blunder of his career. Other mathematicians, working with Einstein's original, unmodified equations, showed that they naturally described a universe that expands or contracts over time. And in 1929, the American astronomer Edwin Hubble provided the observational proof, discovering that distant galaxies are all rushing away from us, and the farther away a galaxy is, the faster it's receding. The universe isn't static at all. It's expanding, and if you run that expansion backward in time, everything, all the matter and energy in space itself, converges toward a single, unimaginably hot, dense point, an origin event that came to be called, somewhat dismissively, at first by a physicist who didn't even believe in it, the Big Bang. Confirmation of this idea arrived almost by accident in 1965, when two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, kept picking up a faint, persistent hiss of microwave radiation in their antenna, coming from every direction in the sky with no obvious source. They initially suspected a fault in their equipment, and famously spent time cleaning pigeon droppings out of the antenna horn before realizing the signal simply wouldn't go away. What they had stumbled onto, without originally intending to look for it, was the cosmic microwave background, the faint, cooled afterglow of the Big Bang itself, radiation that has been traveling freely through space for nearly the entire history of the universe, redshifted and dimmed by billions of years of cosmic expansion into a nearly uniform microwave hiss filling the entire sky. It remains one of the most powerful pieces of evidence we have for how the universe began. And yet, once astronomers started measuring the universe carefully at this scale, two enormous mysteries emerged, mysteries that remain unsolved to this day. First, galaxies rotate in a way that simply doesn't match how much visible matter, stars, gas, dust, they actually contain. Something invisible, something that doesn't emit or absorb light, but clearly exerts gravitational pull, seems to be holding galaxies together, a mysterious substance physicists now call dark matter, making up roughly a quarter of everything in the universe, detected only through its gravitational effects, never directly observed. And second, in 1998, astronomers discovered something even stranger, that the expansion of the universe isn't just continuing, it's actually accelerating, speeding up over time, pushed apart by some mysterious energy inherent to empty space itself. When physicists worked out what kind of mathematical term could produce this effect within general relativity, it turned out to be exactly the cosmological constant Einstein had introduced decades earlier and then abandoned as his biggest mistake. It was back, and this time it wasn't a fudge factor. It was describing something real, now called dark energy, and it makes up roughly 2/3 of everything that exists. Add it all up, and the atoms making up you, and this bed, and everything you've ever touched or seen, amount to only about 5% of the total contents of the universe. The rest, the overwhelming majority of existence, is something we still don't understand at all, quietly waiting, the way blackbody radiation and the Michelson-Morley experiment once quietly waited for someone patient and stubborn enough to finally figure out what it actually is. The evidence for dark matter first became impossible to ignore through the careful work of an American astronomer named Vera Rubin, who spent the 1970s meticulously measuring how fast stars orbit at different distances from the centers of spiral galaxies. If all the mass in a galaxy were accounted for by its visible stars and gas, stars far out at the edge should orbit noticeably slower than stars closer in, the same way outer planets in our solar system orbit the sun more slowly than Mercury does. Rubin found instead that stars far from the center were moving just as fast as those near it, orbiting as though there were vastly more mass present than telescopes could actually see. Her careful, repeated measurements across dozens of galaxies left little room for doubt, and dark matter, once a fringe suggestion, became one of the central puzzles of modern astrophysics. Decades of searching, using underground detectors shielded from cosmic rays, particle colliders, and ever more precise astronomical surveys, still haven't revealed what this invisible material actually is, only that it's there, in overwhelming quantity, gently shaping the structure of every galaxy in the observable universe, including the one you happen to live in. The discovery of dark energy came from two independent teams of astronomers in the late 1990s, racing each other to measure exploding stars called supernovae in extremely distant galaxies, hoping to determine precisely how much the expansion of the universe was decelerating over cosmic time, since gravity, pulling everything together, should have been acting as a kind of cosmic brake. Both teams found the opposite of what they expected. The expansion wasn't slowing at all. It was speeding up, and has been for billions of years. The physicists leading those two teams shared the Nobel Prize in 2011 for a result that nobody had gone looking for, and that nobody, even now, fully understands. We can measure dark energy's effects with real precision. We simply don't know, at the deepest level, what it actually is, whether it's a fixed, unchanging property woven permanently into empty space, or something more dynamic that might change as the universe continues to age. Some theorists have proposed that dark energy might not be perfectly constant at all, but a dynamic field, sometimes called quintessence, that could change in strength as the universe ages, which would carry enormous implications for how the story of the cosmos eventually ends, whether it keeps expanding forever, colder and emptier, or something stranger happens down the line. None of these proposals have been confirmed. It remains, quite genuinely, one of the biggest open questions in the whole of physics, sitting patiently, unresolved, the same way the Michelson-Morley result once sat, waiting for its own Einstein. So here we are, 2,500 years after Thales stood on a Greek coastline and decided that water might be the one substance underlying everything. And after all of it, after Aristotle's falling elements and Galileo's rolling balls and Newton's clockwork universe and Maxwell's unification of light, and Planck's reluctant quanta, and Einstein's bent starlight, and Hubble's fleeing galaxies, we still don't have a finished story. Quantum mechanics and general relativity still refuse to speak the same language. Dark matter and dark energy still make up the overwhelming majority of everything that exists, and we still don't know, fundamentally, what either one really is. String theory and loop quantum gravity both offer possible paths toward a deeper theory that could unite gravity with the quantum world, and neither one has yet made a prediction that's actually been tested and confirmed. This is the unfinished symphony, the open wound at the center of modern physics, and it might stay open for another century, or it might get resolved by someone who hasn't been born yet, sitting somewhere right now. Maybe as unlikely a figure as a patent clerk in Switzerland or a quiet mathematician on a plague-closed farm, waiting for their own version of an apple to fall. But notice something as you lie here now, close to sleep. Notice that none of this uncertainty makes the story feel unfinished in a bad way. It makes it feel alive. Every generation in this story, the Greeks guessing at water and atoms, Kepler trusting his data over his own mystical beliefs, Planck reluctantly introducing a quantum he didn't believe in, Einstein arguing with Bohr for decades and losing every single time. Every one of them thought they were close to the end, and every one of them turned out to be adding one more layer to something far larger than they could see from where they stood. Newton's mechanics didn't get thrown away when Einstein arrived. It got folded in, still perfectly good for launching a rocket or building a bridge, just revealed to be an approximation of something deeper. And whatever comes after Einstein, whatever finally reconciles gravity with the quantum world, won't erase general relativity either. It will contain it, the way a larger circle contains a smaller one. And here's the phrase we've come back to again and again tonight, because it's worth carrying with you into whatever dream comes next. The universe doesn't owe us an intuitive picture. It never promised to make sense in terms of falling apples and ticking clocks and common sense built up over a lifetime of catching balls and watching campfires. It only promised to be consistent, and for 2,500 years, through every wrong guess and every stubborn genius and every quiet, patient decade of doubt, it has kept that promise more faithfully than anything else we know. Feel the weight of the blankets again, the way you did at the very beginning of all this. That weight is gravity, the same force Newton wondered about watching an apple fall, the same force Einstein revealed to be a curve in the fabric of space-time itself, bending gently around you, around this bed, around this entire spinning planet. The photons that carried the last bit of light you saw before your eyes closed tonight traveled, as both wave and particle, exactly as strange and exactly as real as Einstein and Planck first suspected. The atoms making up your own body were forged inside the heart of a star, billions of years ago, held together by the same quantum rules that puzzled Bohr and Heisenberg and Schrödinger. The same rules that are, at this very moment, quietly, effortlessly, keeping you alive without asking for your attention or your understanding. You don't need to remember any of the names tonight. Not Thales, not Newton, not Einstein, none of it. What's worth carrying with you is just the shape of the whole story. 2,500 years of curious, stubborn people asking simple questions and refusing to stop until the universe answered, each one handing what they found to the next generation, none of it wasted, all of it still quietly running, right now, in every atom, in every photon, in every heartbeat, including your own. So let the ideas drift now, the way everything else in this story eventually drifted into something larger. Let your breathing slow. Let the questions rest unanswered for tonight, patient, the way the universe itself has always been patient with us. And let whatever comes next, sleep, or a dream, or just the quiet dark, carry you gently on.